Hello friends, welcome to my channel. Let's have a look at the daily challenge problem. That is problem 1457, pseudo-palindromic paths in a binary tree. So in this video, we're going to share two formats of solutions based on depth-first search. The first format use the set abstract data type, and the second format use bit manipulation. So first, I'll read through the statement of the problem to digest the requirements, and then we do some analysis, and finally we share the two formats of the code. So first, I'll read through the statement. So given a binary tree where node values are digits from 1 to 9, a path in the binary tree is said to be pseudo-palindromic if at least one permutation of the node values in the path is a palindrome. So we are required to return the number of pseudo-palindromic paths going from the root node to leaf nodes. So that's the main body of the statement. So here are three examples. So the third example actually is very special. It contains only a single node tree. So that's there's also only one path, that is none itself. So the return is 1. So in the second example, so only the path from 2 up to 1 is a valid one. So the output is 1. So if we examine other paths like 2, 1, it's not a palindrome up to permutations. So the third path, 2, 1, 3, 1. So the 1 appears twice, but 2 and 3 appears once each. So this is not a palindromic path up to permutation. So in example 1, so the return is 2. So the two paths 2, 3, 3 and 2, 1, 1 are both pseudo-palindromic in the terminology of the problem statement. So with that said, let's also look at the additional constraints. First, the number of nodes in the tree is in the range 1 and 10 to the power 5. So this actually defines the problem size. And the node value is in between 1 and 9. So this is actually an important assumption for this problem. So with that said, let's look at the method we're going to present. So here the method is depth-first search. So the key for this problem is how to check if a root-to-leaf path can be organized to be a palindrome. The criterion is that at most one value appears an odd number of times in the path. So with that realized, actually we are going to present two formats of solutions. The first format actually is going to use the set abstract data type to check the frequencies. So the second operation, or the format 2, is based on bit manipulation. So we are going to use bitwise OR and bitwise AND to do the check. So here are more details. To use set abstract data type, so we actually look at next node in the path. So we're going to check if node value is in the set. If so, we're going to remove the value from the set. So otherwise, we add the value to the set. So in this case, a root-to-leaf path is pseudo-palindromic if and only if the length of the set is less than 2, meaning that at most one value appears an odd number of times in the path. So this is option 1. So for option 2, actually we can use bitwise operations. So we can use an integer s to encode the even-odd frequencies. So when we traverse a node, we mark the bit at position node value to be 1. So this actually corresponds to set s to be 1 shift left to this number of positions. So it also equals 0 exclusive OR with this number. So then when we look at the next child, so we update the s representing the path ending at child to be s equals s exclusive OR with this number. So 1 shift left, so here should be child value. So this is the main operation we're going to do when we do the traversal. So if a value appears even number of times, so respectively odd number of times. So the corresponding bit position in S is 0 or 1. So to check if at most one digit has an odd frequency in the root to leaf path, we just need to check S and S minus 1. So if this number equals 0, so we actually get a path which is pseudo-palindromic, so we increment the counting by 1. So otherwise we just continue. So to digest this check, so we can see, for example, if 3 and 5 both appears odd number of times, so in binary, so we have S is like this, 1 and 1 here. So this is the 2 to the power 3, this is 2 to the power 5, corresponding to the parities of 3 and 5. So then if we compute S minus 1, so in binary format, so we have 1, 0, then this tends to be 0. So we have 1, 1, 1. So this is the result. Then if we compute bitwise add between S and S minus 1, so we are going to have 1 here in the first position, because more than 1 digits appear odd number of times. So this number is not 0. So in other case, for example, if only 5 appears an odd number of times in binary, so we have such a representation. So here in this position, so we have this is 2 to the power 5, right? So then S minus 1 will be 0, 1, and 4, 0 follows. Then if we compute bitwise add, so this is 1, but this is 0. So this is 0, but this is 1. So overall we have 0. So that's the logic here. So that's with that said, we finish explaining the second option. So overall, the main point for this problem is how to encode the frequencies effectively. So before we look at the code, here is an extension. So can you do a solution in the recursion format? Alright, so with that said, we're going to carry out or implement the two operations. So one is using set, and the other is using bit manipulation. The first one might be straightforward, and the second one needs a little bit thought, but it's actually not another representation of the first option. So with that said, let's do the code. So this is option 1. So we're going to use set abstract data type. So for this, we're going to initialize a result whose final state is what we want to return. So in other words, result counts how many pseudo-palindromic root to leaf paths. So this is the one. Another one is a container. So we're going to initialize a container to do traversal of the binary tree. So for the container, we're going to store one is a root, the other is a set. So the set actually counts the frequencies or even an odd for values of the in the path from the root to the current node. So here we are going to add the root value. So this is a set. So in other words, we store a node and a set. So this is the container. So next, basically, we are going to do traversal. So while container. So we're going to do the depth first search. So we're going to so let's see node and the set. So we're going to pop from the tail, so last element. So this, as we are going to append from the tail also. So this container is used as a stack. So then first we're going to check if not node left and not node right. In other words, so this node is a leaf node, and we are looking at the end of a path. So in this case, we just need to check if length d, the set, is less than 2. Then in this case, as we explained, we're going to increment the result by 1 because we found one path which is pseudo-palindromic. So this is one case. In other case, so we're going to add the corresponding information to the container or to the stack here. So if node left, then in this case, so we can actually introduce a temp variable, which is a copy of the previous set. And then what we are going to do is that we check node left value. Because node left is not null, so we can do this check. So if this is in temp, then we can actually remove, right? We can remove this value from the set, node value left. So otherwise, so we just need to add this node value, node left value, same above. So it's node left value. So then what we want to do is that after this check, so we're going to container append this set of information. So 1 is node left, and 1 is the state of the set. So that's temp. So this is one case. So next, we are going to do the same thing actually for the right subtree. So we're going to copy this block and then put it here. Then we change left to be right. So let's change this to be right, and this to be right, this also to be right. So once we've done this, actually after we exit this while loop, it means that we finished the traversal. So we have located all the root to leaf paths and checked if they are pseudo-palindromic. So we just need to return the state of the result. So this is the one format of solution. In this case, in this format, we use the set abstract data structure to check the frequencies. In other words, we record if they are odd or even. So with that said, let's first do a special case check. Yeah, it passes one special case. Now let's do a generic case check. Yeah, it passes all the generic cases. So this is actually one solution. So next, let's copy the class signature and the function signature here. So let's change this solution to be V1. So now we are going to use option 2. So here we are going to use bitwise operations. So for this, actually the procedure is the same, but we just need to use one single number to encode the positions and their corresponding frequencies. So for this, I'm going to initialize a result variable. So this is also counting of pseudo-palindromic root to leaf path. So with that said, here I'm going to specify it's a stack, or you can keep it as a container. So what we're going to put at the very beginning is root and 0. So this is the starting point, because 0, the reason is that 0, so exclusive all with an integer, so it's just equal that integer. So that's the preparation. So now we are ready to do the traversal. So first, we're going to get the node and the path. So we are going to use this number to represent or encode the path, right? So this will be stack pop. So next, what we are going to do is that if so what we are going to do is that we are going to update the path. The path will be let's see, path exclusive all with the this number. So when move to the left, shift to the left, this number position. Sorry. So this one, and then if it's a leaf node, so we're going to check if it's corresponding to a palindromic, pseudo-palindromic path. So if not node left and not node right. So in this case, so we're going to check if at most one digit has an odd frequency. So in this case, we're going to check path bitwise add path -1. So if this is 0, then we're going to increment the result by 1. So otherwise, we just continue, right? So this if block checks the end of the path. Otherwise, so we're going to check or put the corresponding left subtree and right subtree information to the stack. So if node left. Now in this case, so we're going to append the stack to be node left and path. So this path actually is the ending at the parents of node left, right? That's why we first do this operation. But you can write in a format which ending at the current node. So that's a small detail. So similarly, we can do the right? So stack append node right and path. So with that said, actually we finished the bulk of the work. So once we exit this while loop, we traversed the whole tree and we located all the root to leaf paths and checked if it's pseudo-palindromic. Then we're ready to return the result state. So that's the second format of solution, which we use bitwise operations to do the job. So now let's do a special case check. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So I guess that's about it for the two formats of solutions to this problem. Then let's make a small summary to end this video. So in this video, we did two formats of solutions based on depth-first search. So the first format, we used set abstract data type to aid the check of pseudo-palindromic paths. And in the second operation, we actually used bitwise operations, more specifically the bitwise OR, exclusive OR, and bitwise add. So with that said, I guess that's about it for this video. Thank you very much.